how a threat like EMP can affect us as human beings. As we live in an age of technology, everything and anything we do today heavily depends on the electronics. Looking from a digital camera to a television receiver to more sophisticated equipment used into the medical environment, hospitals, clinics, and then the defense installation, to our communication systems, to our safety-related equipment. Everything has some sort of electronics in there. And based on our continued use of electronics and our reliability on the electronics, though it's a good thing, however, it makes us more vulnerable to the phenomena like the EMP. So we're going to explore how EMP could potentially affect, how could it become a threat. A basic definition of EMP is that a very high amplitude, short duration, broadband pulse of electromagnetic energy which can disrupt any electronics it finds in the way. As we know, electromagnetic pulse is produced by a nuclear explosion is not a new discovery. It was known since the earliest days of nuclear weapons testing. The magnitude of the EMP and the significance of its effect, however, were not realized for quite some time. During the first nuclear test done by United States in 1945, electronic equipment was heavily shielded. However, still it led to a lot of the issues with the equipment who was supposed to be recording the signal. Similar disruption of the instruments were recorded by the initial experiments done by the British researchers from 1952 to 1953. The high-altitude nuclear test of 1962 made the increased awareness of the EMP beyond the original small population of the scientists. The larger scientific community became aware of the significance of the EMP problem after a series of the articles which were published in the Electromagnetic Pulse magazine early 1980s. Now we're going to move on to some of the basic physics behind the EMP phenomena. As I mentioned earlier, the physics behind the EMP by itself is a huge topic, and it could take days to talk about how exactly this happens. However, still I try to put it in a very brief manner just to introduce a concept for a listener how this phenomena could potentially happen. A nuclear payload detonated at a very high altitude within or above the Earth's atmosphere causes the gamma rays to radiate out from the explosion. When those gamma rays interact with the atmosphere or the air molecules in the atmosphere, that releases the RF energy. The pictures on the side, the one on the bottom, shows how the gamma rays are radiated out from the charged atoms. And the picture on the top, on the right, illustrates after the explosion how the electromagnetic energy is generated when photons interact with the environment. This process by which from the gamma rays to the photons and eventually the EM field is generated is called Compton's effect. This slide shows a little bit more detailed description of how the gamma rays are converted into what we call the EMP. After the explosion, the electrons which are called the Compton's electrons, being smaller than their corresponding positively charged atoms, travel at a higher rate of speed rapidly increasing the charge separation distance between them. This separation time defines the EMP rise time to peak voltage. The electrons quickly recoil back to their protons to conserve energy. Protons recoil electrons. This recoil time determines the EMP fall time from peak voltage, very, very similar to the way the capacitors are charged in the discharge. This process also resembles closely to how the ESP phenomena takes place. During the explosion, when the gamma rays are radiated out, and eventually the EM energy is created, there are a whole bunch of the bursts of the pulses which are very sharp rise time. Their rise time fall in the range of nanoseconds to few microseconds. A large number of the energy created by these very short duration pulses range in the frequency of 10 megahertz to the 100 megahertz. The thing to note is that a large number of electronic equipment, their processors, their speeds, even used today, lie in that frequency band. Therefore, that poses a higher threat to the electronic equipment we use today. Due to the very high rise time, the electrical field strength of up to 50,000 to 100,000 volts per meter can easily be generated depending upon the nature of the explosion. Another important factor to remember in terms of the EMP or NEMP, which stands for nuclear electromagnetic pulse, is the exposure radius. The concept of the NEMP is that a very high altitude blast takes place. Now, depending upon what is the height of the blast from the atmosphere, what is the size of the blast, what type of explosive is used, all these collectively would determine what surface area on the Earth would be affected by the EMP pulse. The picture on the bottom right corner of this slide shows with radii that if a burst takes place 30 miles from the surface, it will cover a radius of 480 miles. If it takes place about 120 miles, obviously it increases to 1,000 miles. Then if a burst takes place about 300 miles, it's going to cover practically the entire North American region. So that kind of gives a perspective of, with the variation of the amplitude, with the variation of the altitude from the surface of the Earth, how would the EMP would affect the area on the surface. Although the concept of the EMP is primarily related to the nuclear explosion, with the development of the new technologies, with the development of what is very commonly referred as E-bomb, people are coming with the technologies which are called dirty energy weapons. They are capable of producing the EMP effect without a nuclear blast. Some of the examples are an arc discharge EMP generator. Another example commonly used is flux compression generator. On a smaller scale, highly effective non-nuclear technologies, as I mentioned above, are progressing very, very fast. Some of these weapons are today being used by the U.S. Armed Forces and local and state police departments. The flux compression generator typically integrates a small parabolic reflector to direct and focus the pulse energy towards the target. U.S. Navy has reportedly used a FSG pulse weapon in the early hours of the Persian Gulf. Basically, with the help of a similar weapon, they were able to knock out all the communications of the enemy, and that caused total devastation for the enemy. They lost all the communication, and this gave a strategic advantage to the U.S. with the use of this FSG. Why do we need to perform testing? We talked about how the EMP happens. EMP could come from a nuclear blast, of course, which is the conventional concept. EMP could happen from some of the newer technology where no explosion is needed. So based on the threat, based on the concerns that these risks are real and they can cause serious, they can have serious implications on the electronic products used for essential services, especially for the defense applications. U.S. military came up with a test methods over almost like 50 years ago. These tests were being conducted under different standards. Today, the most commonly applicable standard is MIL standard 461. The latest version is version F. However, large number of people are still using both version E and F. The idea of the testing there is to determine the device vulnerability. The idea is to determine whether a device or system can handle the effect of an EMP should either there be a nuclear blast or should somebody use what we call EMP or FCG-like devices. At the same time, this sort of testing gives a better understanding to the manufacturer of the electronic equipment used in the defense application, that what sort of design improvements they would be required to do to make sure these devices continue to operate as they are intended to. As I mentioned, MIL standard 461 ENF provides a test methodology. MIL standard 461 primarily looks at the aspect of the what we call radiated effect of the EMP, which is covered by RS105. However, RS105 does not cover the effect of the conductive coupling of the signals on the IO line. Indirectly, that is covered by another test which is called CS116, where multiple frequency signals from 10 kilohertz to all the way up to 100 megahertz are applied on the IO lines and on the power lines. And the idea there is to see if the EMP phenomena happens, how would it affect the cabling system. Although the main focus of this presentation is going to be primarily on the RS105, I would still draw with a couple of slides a brief comparison how RS105 and CS116 correlate. As far as the applicability is concerned, RS105 testing is generally applicable to equipment installed to either fully exposed and partially exposed environment. U.S. Navy requires RS105 testing to be done on nearly almost all of their installations, with the exception of the submarine. This testing applies to Army aircraft for safety critical equipment. It applies to the equipment of the non-metallic platform. It applies to the enclosures located external to the shielded platform or the facility. Continuing on, I want to show how the EMP pulse looks like. EMP pulse is a double exponent per 461. The amplitude has to be as high as 50,000 volts per meter. However, standard specifies testing should be done in steps. We start testing in the lab environment with 10% of the peak amplitude, and then we increase the amplitude in the steps so that we could determine what level the susceptibility starts taking place. If we apply the surge signal, if we apply the EMP signal right at the maximum peak voltage, the possibility of the device getting permanently damaged is way too high. Therefore, standards specify the testing should be done in steps starting from 10%. And 5 pulses are applied with 1 pulse per second, with 1 pulse per minute, and the signal is applied to all 3 axes of the product. A little bit more about the test procedure. As I mentioned earlier, we start with the test 10% of the specified level. Using a very high bandwidth oscilloscope, the waveform is verified. Typical E-field generators, which are used for the EMP generation, would have the field from the top plate of the generator to the bottom, meaning vertically down. Therefore, device would have to be rotated to all the axes so that it's been fully exposed and all the surfaces of the device have been investigated to check for the signs of susceptibility or vulnerability. And on the each side, the signal is applied 5 times. There are quite a few commercially available test methods, test setups in the industry. Some of the very commonly used are based on CEM cells and or transmission line cells. On the screen, on the top left corner, it's a commercial setup available to do the RS105 testing. On the bottom right corner, the picture illustrates the setup we use at MetLabs in California. The next slide shows a very, very similar design. However, the beauty of this design is that this setup, it's a very similar concept to the transmission line. The beauty of this setup is that it could be wrapped up, put up in a box, and it doesn't take any space in the lab environment. And when somebody needs to perform the testing, you take it out from the box, takes a couple of hours to do the setup, and then you are ready to go. The next slide will show the top view of this structure. The load on the right-hand side is a bunch of the resistors in series, which form up the appropriate impedance required to have the appropriate matching. The test zone is the area immediately left to the bluish line in the middle of this slide. It's extremely important that the EUT is within the test zone per the dimension specified or by the design of this antenna. Having a larger EUT sitting there could significantly compromise the waveform of the RS105 signal. This is another example of another commercially available setup. This sort of setup is used for extremely small shoe box-like products. For larger products, we would have to still rely on a setup like transmission line method. Now, towards the end of my presentation, I'm going to draw a brief comparison between CS116 and RS105. As I mentioned earlier, RS105 takes care of the radiated aspect of EMP phenomena, as it would happen when nuclear detonation takes place or somebody is using some of the E-bomb-like technology. However, the intent of that test is to just explore the physical structure or the box we are testing, it purposely ignores the coupling which would happen during this phenomena to the IO line and or the power line. So much so, the RS105 says that during the test setup, arrange your cables, arrange your IO lines in such a way that you would minimize the impact of the coupling onto the IO line. To explore the effect of the coupling, which would happen eventually conductively on the IO line, CS116 test is performed, which resembles in waveform to some extent to the waveform for RS105. There, multiple frequency signals, 10 kilohertz, 100 kilohertz, all the way up to 100 megahertz are inductively applied to the IO lines and or the power lines. And this way, we simulate the effect of the EMP signal, which could couple to the IO lines and could travel the way back to the box. Whereas RS105 will take care of the box itself or the housing of the product itself. It will test the effectiveness of the shielding of the box or the housing which is holding the product. However, the threat of the signal traveling onto the IO line and the quality of the filtration being used at the input-output line is verified using the test methods according to CS116. My next slide is to talk about some of the limitations of the test method itself as it's described in RS105. RS105 throughout the document, especially in the first few pages where it talks about the general test setup, it specifies the testing. During the testing, the product should be set up as it would be installed at the final installation. The grounding should be done the way it will be grounded at the final platform, whether the product is bolted right onto the metallic platform, whether it uses a ground braid or it uses any other technique for the grounding purposes. That, in a way, indirectly could have serious implications on the test results. Let's assume we are testing a device which runs some sort of load, and that load is grounded at the load end. In this situation, when the RS105 signal is applied, a large portion of the current will flow on the shield of the cable and will go towards the lower impedance, which is the ground connection, which in other words would under test the product. There are, however, means to mitigate the problem. Typically, in the lab environment, we use either ferrite chokes or some other appropriate filters to those interfaces if commercially available, so that the signal do not flow towards the ground point and it stays more onto the product itself, and thereby the product is exposed to the test level as intended by 461. The second limitation is the 461. The intent there is to minimize the effect of the signal, the EMP waveform, onto the cable, as RS105, I mentioned earlier, does not want to purposely cover the effect on the cable. So they specify lay out the cables in a way that it would minimize the effect of the EMP signal onto the cables. However, in large number of cases, due to the practical reasons, it's not possible practically, or it's not feasible the way the cables are designed. Oftentimes in the lab environment, the test houses run into the trouble where cables still get affected. There are ways around it. You can shield the cable, you can double shield the cable. However, using the shielding other than the shielding recommended by the manufacturer could also raise questions about the validity of the test, whereas where we have modified the test sample. Another issue there is that there are not too many horizontally polarized EMP simulators. As I mentioned earlier, testing would have to be done in a way that all the three orientations of the device are covered. That eventually requires rotating the device at 90-degree angles after each test. It has its own practical implications. In some cases, it's not even practical to rotate the device and still get the functionality the device is supposed to do. So in that sense, 461 RS105 does continue to prove a very, very challenging test where it would require a long involvement from the test house with the manufacturer and the end buyer to come up with a test plan which would still meet the intent of the testing as specified by 461. Okay. Some of the design considerations. Obviously, the very first thing comes to mind is the apertures, the seams, the holes. Care should be taken to address all the above. There shouldn't be any holes which are not necessary. In some cases, you want to have the hole like for the filters, like you have to have honeycombs. If the holes are needed for ventilation, for cooling down the product, or for whatever reason, they need to be, the hole size need to be carefully considered against the beam width of the fastest signal pulse, which could potentially go through that hole and possibly affect the electronics inside. Similarly, special attention needs to be given to the seams to make sure there is a continuous metal-to-metal or electrical connection. There are ways to do that. People use precision machining. You could use specialized gasketing. Many other people use specialized foam-like material to provide additional shielding to the seams and the joints and the holes. In many cases, it comes really handy to perform the analysis before going to the actual testing, to fully understand and to fully visualize the vulnerability of the design we are testing. There are other cases where the products have the displays. They have LED panels or keyboard or other access panels. In those cases, it may become necessary to use thin metal coating on all those displays, screens, windows, whatever, to ensure a better shielding. Another question which comes to mind, and it's still an open question, and there's an ongoing debate in the industry on that. Even though we say we take the opinion that CS116 will take care of the coupling effect of EMP signal on the IO line, but it does not exactly address, nor there is enough statistical data to clearly indicate that if the CS116 levels will be the same as the coupling which will be caused by the RS105 or the EMP waveform itself in a practical environment. So to ensure that doesn't become an issue on the I/O lines, it's a very good practice to use a much higher factor of safety in the calculation. Okay, we are getting very close towards the end of my presentation. I have 2 more slides to talk in very general terms about how to make our customers' experience more comfortable when a customer comes to our lab for testing. And at that point, we can start the question-answer session. Okay, so my second last slide is how to better prepare for your EMC testing, how to make the EMC testing more efficient experience when you come to the lab. Number one is, as always, we highly recommend to our customers to pay close attention to the configuration. Make sure you clearly identify what configuration you plan to test. There needs to be operational monitoring method which is valid for the applicable standard. For example, RS105, there need to be some means to know if the device takes a hit, if the device is susceptible or vulnerable during the RS105 and or CS116 testing. How would an operator or a test technician know the device is seeing a degradation of the performance? So there need to be a clearly defined test method before we start the actual testing. And the final item there is to properly cable the UT to ensure all the ports which are supposed to have cable in the final installation should have the cables with the same kind of shielding they would be using in the installation in the field. Without that, without having the appropriate shielding, people can run into any number of problems. In some cases, the whole test could come into the question. Okay. Now my final slide is how can MET assist? We work with our customers. We offer free lunchtime reviews to our customers where our experts can sit with the customer, look onto their product, discuss about the practical limitation and issues, go over the test plan. We offer working with our customer and their buyer to finalize a test plan and identify the areas which need to be tested to clearly before the testing begins. With that, I will conclude my presentations. Barnaby, I'm going to toss it back to you to see if there are any questions and see if we can start the question-answer session.
Yes, thank you, Asad. That concludes the presentation portion of this webinar. This webinar has been recorded and will be available for on-demand viewing on metlabs.com. Now we will go ahead and answer questions. If you have a question, please type it in the questions area of your control panel. For all relevant questions, we will read the question, then give a verbal answer. There might be a minute or two pause while we wait for questions to come in.
Okay, there is one question about the RS105 applicability, whether it's required by anybody other than the U.S. government. So the answer is yes. Quite a few organizations in the private sector would want this testing to be done based on the nature of the business they are into. In addition to that, the thing to remember is 461 is not a standard used in the United States only. It is widely accepted worldwide by the nations like Australia, Italy, Turkey, many other countries would want their product before they purchase from any of the vendor in U.S. To have the product tested to 461 and or RS105. So even in those cases, the product would have to be tested to RS105 requirements. But I believe that's all on the questions side. So with that, it concludes the question answer session. If you folks have any other questions, or if Matt could help you assist with your upcoming testing, please feel free to contact our marketing and sales team. Thank you very much. Thanks for your time. Have a good day.